This is the 2011 AMC 8 solutions. So we'll start with the first problem. Margie bought 3 apples at 50 cents per apple. If she pays with a $5 bill, we want to know how much change she gets. So she starts with $5, and we're going to subtract 3 times 50 cents. So that's equal to $5 minus $1.50, and that's equal to $3.50 in change. So that's the first problem. Problem 2, we have that Carl's rectangular vegetable garden is 20 by 45, and McKenna's is 25 by 40. And we want to know which of the following statements are true. So if we take a look at the statements, they're all relating to the area, so we'll want to calculate those. So for Carl's, it's going to be 20 times 45, which is 900. And for McKenna, it's going to be 40 times 25, which is 1,000. So that means that McKenna's garden is going to be larger by 100 square feet. Okay. Problem 3. We have that we want to extend the pattern of 8 black and 17 white tiles by attaching a border of black tiles around the square. And then we want to know the ratio of black to white tiles in the extended pattern. So we're given that there are 8 black and 17 white, and we want to know the ratio afterwards. So we're going to need to know how many black tiles we add. We add 5 on each side, which would be 20 for all 4 sides. And then, so that's 2 sides, right? So we're gonna add 20, and then we'll also add 4 corners. So that's gonna be another 4. And that's a total of 32 black tiles. And we haven't changed the number of white tiles, so that remains 17. So we have 32 to 17. Oh wait, no, did I? Black to white tiles. Did I mess something up? I might have the wrong answers. I think this is correct so far. Yeah, that should be right. Okay. We have the list of numbers of fish that Tyler caught in 9 outings last summer. And we want to know which statement about the mean, median, and mode is true. Okay. So the first thing we'll calculate is the mean. We have 9 outings, so we just want to add up the total and divide by 9. So 3, right, 2 plus 1 is 3, plus 3, plus 3, plus 3, plus another 3, that's 15. We have 15 divided by 9, which is also 5/3. So that's going to be our mean. Now to find the median, we're going to have to put all the numbers in order. So 0, 0, 1, 1, 2, 2, 3, 3, 3. And then we just have to find the middle number. So if we just find the 5th number, that's 2. There are 4 numbers on either side, so we know that the average is 5/3, median is 2, and now let's find the mode. The mode is the number that appears the most often, so that's 3. So just putting them in order, 5/3, 2, 3. 5/3 is less than 2, so this is the correct order. and that points us to mean, median, and then mode. Okay. Now we want to know what time was it? 2011 minutes after midnight on January 1st, 2011. So the first thing we want to do is convert these minutes into hours. So let's do that by dividing by 60. If we divide by 60, then we will get 30. Let's just do the division. 2011, put a 60 here, a 3, and then that's 180. And that leaves us with 31 minutes. So, wait. Yeah. And so we can put in another 3, and that would be another 180, and that leaves us with 31. So now we have 33 hours and 31 minutes. And the first 24 hours will correspond to 1 day, while the other 9 hours and 31 minutes will correspond to 9:31 a.m. So we're looking for 9:31 a.m. on January 2nd. Okay. Let's keep going. We have a town of 351 adults where every adult owns a car, motorcycle, or both. We want to know how many of the car owners do not own a motorcycle. This is going to be a Venn diagram problem. Let's say this is the car owners, this circle, and this is the motorcycle owners. So we'll use a small c for just car owners, a B for the ones who own both, and motorcycle, small m for that. So we know that the total is 351, which would be C plus B plus M. And because we want to find C, we'll want to find B plus M. And we know that B plus M is just the number of adults who own a motorcycle, which is 45. So we know B plus M equals 45. And now we can do a very nice subtraction here, leaving us with just C and 306. So our answer is D, 306. Okay. Problem 7. We have 4 congruent squares, which are each divided into congruent triangles or rectangles and partially bolded. We want to know what percent of the total area is partially bolded. So we have a total of, we'll say, 4 big squares. We want to know how many big squares are shaded or bolded. In the first one, 1/4 of a big square is bolded. In the second, we have 1/2 of 1/4. This is 1/2 of 1/4. So we have 1/8. In the next one, we have a full fourth and another eighth. That's going to be 1/4 and 1/8. Alternatively, we could have just written 3/8. And in our last one, we just have another 1/4. So our numerator is 1/4 plus 1/8 plus 1/4 plus 1/8 plus 1/4. 2/8 is equal to 1/4, so we have 4/4, which is just 1. So this is equal to 1 big square over 4 big squares, which is just 1/4. And that means that 25% of our total area is bolded. Okay, question 8. We have a bag A, which has 3 chips labeled 1, 3, and 5. Bag B is labeled 2, 4, and 6. We draw 1 chip from each bag, and we want to know the number of different possible values for the sum. So the first thing to notice, obviously, is that we have all the odds in one bag and all the evens in the other. So when we pick, we're definitely going to get 1 even and 1 odd, and that's going to add up to an odd number. So we can safely ignore all the evens. So we'll start by looking at the smallest number we could get, which is 3, as well as the largest number we could get, which would be 5 plus 6, or 11. And then we just have to check that we can achieve every single odd number in between, which we can. Right, 5 we could do 2 and 3, 7 we could do 3 and 4, 9 we could do 5 and 4. And obviously some of them, there are multiple ways to do it, but we just want to know how many different possible values for the sum, not necessarily how many ways there are to do it. So we have 5 values. Okay. We have that Carmen takes a long bike ride on a hilly highway. We have the number of miles traveled during the time of her ride. We want to know what her average speed is for the entire ride. So because we're looking at just the entire ride, the only point we care about is the end point. We don't care if it went like that, like that. It doesn't really matter. Actually, we would have to make sure that we didn't go past the endpoint, so maybe something like that would also work. The only thing that matters is that we traveled 35 miles in 7 hours. So to find the miles per hour, we just do 35 miles divided by 7 hours. And that's equal to 5 miles per hour. Okay, question 10. We're told that the taxi fare in Gotham City is $2.40 for the first half mile, and 20 cents for each additional tenth of a mile. We plan to give the driver a $2 tip, so we want to know how many miles we can ride for $10. So the first thing we'll do is set aside $2 for the tip, because that doesn't get us anywhere. So we're left with just $8 to get as far as we can. First, we'll have to pay $2.40 to go half a mile, which leaves us with $5.60. And we've traveled half a mile. And now we'll spend the rest of it for tenths of miles, basically. So how many times does 20 cents go into $5.60? Well, that's the same as 560 divided by 20, which is 28. So we can go 28 times 0.1 miles until we run out of our $10. So that gets us an additional 2.8 miles. This half mile was 0.5 miles. So we just add them up, and we have 3.3 miles. Okay. Let's keep going. Problem 11. We have a graph that shows the number of minutes studied by Asha and Sasha in 1 week. We want to know, on average, how many more minutes per day Sasha studies than Asha. So first we'll start with Monday. We know that Sasha studies an extra 20 minutes on Tuesday. Or that's not 20 minutes, that's 10 minutes. Make sure we're watching our scale. All right. On Tuesday, Sasha studies for 10 fewer minutes. On Wednesday, she studies for 20 more minutes. On Thursday, 30 more minutes. And then on Friday, 20 fewer minutes. So in total, this is 30 minutes extra because the 10s and the 20s cancel out. And because we were looking for average per day, we divide this by 5 days for an average of 6 minutes extra per day. Okay, problem 12. We have Angie, Bridget, Carlos, and Diego. We'll just call them A, B, C, D. They're seated at random around a square table, and one person is on each side. We want the probability that Angie and Carlos are opposite each other. So because it's a square table, it's completely symmetrical. Doesn't really matter where Angie sits. We'll just put her at the bottom. Then in every case, Carlos will either be in this spot, or this spot. And only one of those 3 spots satisfies our conditions. So we just have a 1/3 chance. Okay, let's keep going. We have 2 congruent squares, ABCD and PQRS, each with side length 15. They overlap to form a 15 by 25 rectangle, and we want to know what percent of the rectangle is shaded. So let's label some sides, 15. And we know AQ is 25. We also know that AB and PQ are each 15. So this is 15, and this is 15. So this 30 includes PB twice. And we know that if we only count it once, that's AP plus PB plus BQ, that would be 25. Right, so AP plus PB plus BQ equals 25. But we also know that if we just add PB, then we can do AP plus PB and BQ plus PB, each of which are 15. So that would get us to 30. So that means that the PB that we added has to be 5. So we have to have a 5 here. We want to know what percent of the area of the rectangle AQRD is shaded. So the area of AQRD is 15 times 25, since we're given the dimensions. And the rectangle that is shaded is 5 by 15. We can cancel 15, and we're left with just 1/5, or 20%. Okay. Problem 14. There are 270 students at Colfax Middle School, where the ratio of boys to girls is 5:4, and then 180 students at Winthrop Middle School, where it's 4:5. They have a dance, and all students from both schools attend. We want to know what fraction of the students at the dance are girls. So in the first school, we're splitting 270 students 5:4, so 5 parts to 4 parts. That's also another way to think of it is splitting it into 9 parts and then taking 5 and 4. So we'll think of it that way and divide this into 9 parts of 30 students each. And so we have 5 parts of 30 and 4 parts of 30, which is 150 to 120. For the other school, Winthrop, I'll do a similar operation, first dividing it into 9 parts, and then taking 4 parts and 5 parts. Now, when we have the dance, we're just gonna combine them for a total of 230 boys and 220 girls. So in total, we have 220 girls divided by 450 people, which is also 22 over 45, just canceling the 0. So we have C as our final answer. Okay, problem 15. We want to know how many digits are in the product 4 to the 5th power times 5 to the 10th power. So 4 to the 5th power is also equal to 2 squared to the 5th power. And using our exponent rule that a to the bth power to the c is equal to a to the b times c. We can translate this into 2 to the 2 times 5, which is also 2 to the 10. And now we'll finish by doing 2 to the 10th times 5 to the 10th. It's also equal to 10 to the 10th. And this is just 1 followed by 10 zeros for a total of 11 digits. Okay, so I used 2 exponent rules here. First one, a to the b to the c is equal to the a to the b times c. So this, the reason for this is that I'll do a to the b times a to the b times a to the b. Let's say we do this c times. This is just equal to a to the b plus b plus b, and we can do this c times. So that's also just b times c. And of course, this uses the exponent rule that a to the b times a to the c is a to the b plus c. So if we have the same base, we can add exponents. The other exponent rule I used is that when you have the same exponent, you can just multiply their bases. And reason for that is that 10 to the, well, 2 times 5, 2 to the 10th times 5 to the 10th, we can put a parentheses like this. And then it's pretty easy to tell that they're equal. So this is going to be equal to this. Okay. Problem 16. So we have A, which is the area of a triangle with sides 25, 25, and 30. And then we have B as the area of a triangle with sides 25, 25, and 40. Want to know what the relationship is between A and B. So let's start with the 25, 25, 30. We draw a perpendicular line. Because this is an isosceles triangle, the left half and the right half should be congruent, even if my drawing doesn't seem like it. So we'll split this 30 into 15 and 15. Now with the Pythagorean theorem, if this is our height, we have 15 squared plus h squared equals 25 squared. So evaluating that, we have 225 plus h squared equals 625. Now from that, we can get that h squared is equal to 400, which also means that h equals 20. So we have our height, it's 20. So to find the area of A, we have 30 times 20 divided by 2. We're just using base times height divided by 2, and we get 300. Now let's look at triangle B. So this one's going to be wider, but we still have our 25s. Again, we can do the same thing, and we'll split the 40 into 20s. So now we could go through the Pythagorean theorem again, but if we look up at triangle A, we actually see that we have the same triangle. We had 25 and 20 and 15. And because these are both right triangles, we can use basically the logic from the previous problem in reverse to get that the height is 15. So we actually have here our triangles that are sort of rotated and then mashed together. So the area for this triangle is going to be 40 times 15 divided by 2, which is also 300. You could, yeah, you could go through with this calculation, but you could also just notice that it's the same two triangles just rotated and put together in a different arrangement. So that would make it really clear that A equals B. Okay, we have W, X, Y, and Z, which are whole numbers. We're told that 2 to the W times 3 to the X plus, or not plus, times 5 to the Y times 7 to the Z is 588. We want to know what this expression is. First thing we'll do is start a factor tree. So 588, we'll start by dividing by 2. We can divide by 2 again. We can divide by 3 because the digits add up to 12. And finally by 7. Okay. So we have 2 squared times 3 times 7 squared. That also means that W equals 2, X equals 1, Y equals 0 because 5 to the 0th power is 1, and Z equals 2. If we plug this into our expression, we have 2 times 2, which is 4, plus 3 times 1, which is 3, plus 0, 0 times 5 is 0, and 2 times 7, 14. So our total is 21. Okay, problem 18. We have that a fair six-sided die is rolled twice. We want the probability that the first number is greater than or equal to the second number. So we kind of have two cases in this problem. We have the numbers are different and the numbers are the same. So we have diff and we have the same. So whatever the first number we roll is, the second roll has a 1/6 chance to be the same number. One number that's the same out of 6 possibilities. So there's a 1/6 chance to be the same, and that must mean that there's a 5/6 chance to be different because it has to be one or the other. So if they're the same, there's a 100% chance that the first number is greater than or equal to because they're equal. So we have 1/6 locked in for our probability. Now, if they're different, our probability of being greater is just 50-50. It's either greater or it's smaller. So that's going to be 1/2 chance. So that's equal to 7/12. This part is 5/12, and this part is 2/12. So our answer is 7/12. Okay. Problem 19. We're asked how many rectangles are in the figure. So we kind of have 7 sections, right? If we break it down all the way to the smallest sections, then there's 7 of them. Y is, okay. So we have 1, 2, 3, 4, 5, 6, and 7. So we can sort of group our rectangles by how many sections they have. Starting with the smallest ones, we have that 2, 5, and 6 are all rectangles on their own. So we'll call those small because they're just one section. And next, let's go to medium, which would be two sections. So we have 5 and 6, 2 and 5. We have 6 and 7, 4 and 5, as well as 1 and 2. So if you combine the two sections that are listed, you'll get a new rectangle. That's a total of 5. And finally, let's look at the large ones. So we'll start by seeing if there are any with 3 sections. But no matter how you pick your 3 sections, you always end up with not a rectangle. Sometimes it's an L shape. If you try 2, 5, 6, you could get something wonky like 1, 2, 3 with like this weird thing on the right side. But either way, you won't find anything with just 3 sections. So then we'll try 4. If we do 1, 2, 5, 6, there's 1, 2, 3, 4, 5, and finally 4, 5, 6, 7. I feel like the large triangles are usually the ones that stand out the most at the beginning of the problem. It really does look like this square intersected with these two rectangles. So I feel like those are the easiest to see. But if we add these all up, 3 plus 5 plus 3 is 11. Okay, problem 20. We have this quadrilateral, which we're actually told is a trapezoid. We have a bunch of side lengths and the altitude, which is 12. We want to know what the area of the trapezoid is. So you can see AD is 15, AB is 50, BC is 20. So first thing we'll do is consider what the area formula for the trapezoid is, and that's going to be the average of the bases multiplied by the height. And our height in this case is 12, since that's given to us. Now let's try to find what the other base is, CD. That's the one side we don't know, since we know AB is 50. Okay, so if we draw these perpendicular lines, then we make this rectangle. So this part in between is 50. It's the same as AB. Now we need to find what these extra side lengths on each side are. This is 12, and so is this, because they're both altitudes as well. So we have this right triangle. I'll call this x. We're told that 12 squared plus cx squared equals 20 squared. So let's solve that. We have 144 plus cx squared equals 400, which means that cx squared is 256, and cx must be 16. So if we use a similar method on the left side, we have dy squared plus 12 squared equals 15 squared. So dy squared plus 12 squared equals 15 squared. This is 144. This is 225. And we still have dy squared. So subtracting 144 from both sides, we have dy squared equals 120. No, not 121. 81. And that means that dy is 9. So if we add up all three of our numbers, we have 75. So the sum of our two bases is 125. And now let's properly solve for it. We have the average of our bases, which is 125 divided by 2. multiply by our height, which is 12. Let's cancel this 2 since it avoids fractions. And just 125 times 6 is relatively straightforward. We have 750. Okay, problem 21. We have 10 students, and they're all guessing Norb's age. So Norb says, at least half of you guessed too low, 2 of you are off by 1, and my age is a prime number. So because there are 10 guesses and half of them are too low, we can eliminate the bottom 5 guesses and just deduce that Norb's age must be greater than 36. Now we're also told that 2 of you are off by 1. So if student A's guess and students B guess are both off by 1, since no 2 people guessed the same number, they must have both guessed on either direction of the number. So like x plus 1 and x minus 1. So we're looking for 2 numbers that are off by 2 from each other, and then the number in the middle would be Norb's age. So the 2 possibilities for that are 3638 or 4749. The last piece of information is that his age is a prime number. So we just have to see 48 and 37. Since 37 is a prime number and 48 is not, we know the answer is 37. Okay, problem 22. We want to know the tens digit of 7 to the 2011th power. So let's start by keeping track with a table and hope for a pattern. So we 7 to the 0th power is 1, but I'll write in a leading 0 to show the tens digit is 0. We go to the next power, we have 7. Again, I'm writing in the leading 0 to show you the tens digit. 7 squared is 49. 7 cubed is 343. And 7 to the 4th power is 2,401. So now we have something very interesting. 7 to the 4th power ends in 0, 1. So that actually means that our pattern has repeated. Every 4th number ends in 0, 1. So what this basically means is that all the powers that have an exponent that's a multiple of 4 will end in 0, 1. Let's just look for the closest multiple of 4 to 2011. When I say closest, I'll go for the smaller one. So 2008, so 7 to the 2008th power would be ending in 0, 1. So from there, we'll go for the 2009th power, 2010th power, and finally 2011th power with a 4 in the tens place. And if you, even on the test, if you couldn't figure this out, but you did have this chart written out, you would probably notice that only 0s and 4s are showing up. So you might just take a 50-50 guess, and that would give you pretty good odds anyway. Problem 23. We want to know how many 4-digit positive integers have 4 different digits, not starting with 0, but is a multiple of 5 and has 5 as the largest digit. So we sort of have 2 possible cases, depending on what we're ending in. So in the first case, we'll end with 5, and in the second with 0, since we have to have a multiple of 5. Now, for the other 3 digits, we can't have anything greater than 5, so we're restricted to just 0, 1, 2, 3, and 4. For our first digit, we have 4 choices because we cannot use the 0. So we're restricted to just 1, 2, 3, or 4. For our second digit, we can't use the same digit we used to start because we have to have different digits, but we can use the 0 now. So we've lost one digit and gained one digit, so we still have 4. The next one, we're not gaining any digit, but we did use 1. So we're left with just 3 choices. So 4 times 4 times 3 is 48. In our second case, we have 1, 2, 3, 4, and 5. We have to use the 5, so that's the largest digit, and we don't have to worry about the 0 anymore. So we have 3 choices for where the 5 goes. Let's just box that. Doesn't really matter anymore. Just plop the 5 here. And then for one of our other digits, we have 4 choices. We can pick from 1 through 4. And for the other digit, we just have to pick from the other 3. So we have 4 times 3 times 3. This boxed 3 is the position of the 5. And that's 36. So 48 plus 36 gives us our final answer of 84. All right, problem 24. We're asked how many ways 10,001 can be written as the sum of 2 primes. So you know that most primes are odd, except for 2, right? And now one thing that we notice is that 10,001 is odd. So if we add 2 odd primes, we're using O for odd and E for even. So if we add 2 odd numbers, we get an even number. And 10,001 is not an even number. So the only way to get an odd number is to add an even and an odd, and maybe get 10,001. Because the only even prime is 2, we know that the even has to be 2. And we can pretty easily see that the odd has to be 9999. So pretty much everything just depends on if this is prime, which it's not. It's obviously divisible by 9, because this is 9 times 1, 1, 1, 1. So since there's no way to do it with 2 as one of the primes, and we have to have 2 as one of the primes, there's just 0 ways. Okay, problem 25. We have a circle with radius 1 inscribed inside a square and circumscribed about another square. So we're inscribed inside the big square, and we're circumscribed about the smaller square. We want to know what fraction is closest to the ratio of the circle's shaded area to the area between the 2 squares. So let's draw the center point. We know the radius is 1. So similarly, drawing a radius this way, it's also 1. So we have that the side length of the square is 2. Therefore, the area of the square is 4. Now, let's look at the area of the smaller square. We draw a third radius. We basically, or why not just draw all 4? We have 4 triangles, each of which has an area of, well, let's calculate it. Base times height divided by 2. So 1 times 1 divided by 2 is just 1/2. So 4 triangles with an area of 1/2. Let's call the small triangle's area, which I'll use little a. Let's say that's 2, because it's 4 times 1/2. So back at the question, we need the ratio of the circle's shaded area, the area between the 2 squares. The area between the 2 squares is just the area of the large square minus the area of the small square. So we're looking at 4 minus 2, which is 2. So we have our denominator. Now let's look at our numerator. The area of this circle we can calculate with the formula pi r squared. And our radius is 1. So our area is pi times 1 squared, which is just pi. And the the circle's shaded area is pi minus this square, which we already said was 2. So the shaded area is pi minus 2. And now divide this by 2, since that's the area between the two squares, and we have to approximate it. So let's use 3.14. Hopefully that's enough decimal points or decimal places. Let's see. This is equal to 1.14 divided by 2, which is, yeah, all of these are approximations, by the way. So we have approximately 0.57. So that's close to 1/2. Okay, so those were all the problems from the 2011 AMC 8. Okay, thank you.